Now, the fact that we have this interesting commutation relation between our Hamiltonian and these angular momenta has some very important implications that are interesting for us to think about. Because after all, we are experts on two general theorems that apply whenever we know the value of a particular commutator. In particular, the generalized Heisenberg uncertainty principle then tells us that the product of the uncertainties of the Hamiltonian and the angular momentum must be at least zero, right? And in fact, it's theoretically possible for this product to be zero. It is theoretically possible. There's nothing preventing us from finding a state that is simultaneously a pure state with no uncertainty in energy or in momentum. So we could possibly have a pure state with respect to both of these operators simultaneously. That's a very key fact and can come in handy later on in our analysis. The other thing that we know came from Ehrenfest's theorem, right, which tells us that the time derivative of the angular momentum, right, must be equal to the expectation of this commutator divided by, I times h bar. But because the commutator is zero, this meant that the angular momentum is conserved. Now, there's a very interesting series of connections we can draw here. I want you to notice, right, that the angular momentum is precisely the operator that generates these rotations. And because we have rotational symmetry, immediately we know the angular momentum that's associated with that symmetry is conserved. We had previously, for example, seen that the momentum operator generates translations. And so if we have translational invariance, we know then that the momentum immediately must be conserved. And even if we think about energy, it is the Hamiltonian operator that we use to move our wave functions forward in time. And so if our system is invariant with respect to time, with respect to so-called, say, time translation invariance, then we know immediately that the Hamiltonian, that operator itself, must be a conserved quantity. So there's this deep connection between symmetries, the physical operators that are associated with those symmetries, and the conservation of those operators. And that is something known as Noethers' theorem. And what we have here, in essence, is a proof of the quantum version of Noethers' theorem. We've done it explicitly here for angular momentum, but the argument is the same for the other operators. And this is something that's often proved in your classical physics classes, but in a sense, since we have it proved here quantum mechanically, and we have the correspondence principle, you now also, of course, have a proof of Noethers' theorem, even for classical systems.